Model deployment is the point where a trained model stops being just an experiment and starts serving real predictions. The focus here is the gap between building the model and making it available in a reliable system. The development work from training data through evaluation is the core logic of the model. It combines machine learning knowledge with domain expertise, and that is why ML and data science teams often own this part of the pipeline. The figure separates the pieces that belong to model logic itself. Training data, feature extraction, model building, and evaluation all sit on the development side before deployment becomes the main concern. That label matches the parts we just described. The model is not a single object, but a collection of decisions and processing steps that work together. Deployment usually means moving a model out of the development environment and into a place where other systems can reach it. A staging environment is for testing, while production is where users depend on the model for real work. Production does not mean the same thing for every team. For some, it is a notebook that produces business-facing output. For others, it is a service that must stay available for a huge number of requests with strict reliability. A basic deployment wraps prediction logic behind an HTTP endpoint, packages the runtime dependencies in a container, and runs that container on a cloud platform. That gives other applications a way to call the model through a network request. The route decorator exposes a post endpoint at /predict, and the function reads input data from the JSON body. The model runs on that input, converts the result to a list, and returns the predictions as JSON with a success status code. Once the endpoint is exposed, another application can send a prediction request and use the returned result immediately. That is what makes deployment useful. The model becomes a service that other systems can depend on. The difficult part is operating the model under real-world constraints. Serving millions of users, meeting millisecond latency, catching failures quickly, and shipping fixes safely all require infrastructure and process, not just a good model. Some companies keep development and deployment together, while others hand the exported model to a separate team. The second setup can slow feedback and make debugging harder because each change has to cross more boundaries. The next idea is model export, which is the bridge between a trained model and another application that needs to run it. Exporting usually means saving both the model structure and its learned parameter values. The structure defines the architecture, and the parameters store the trained knowledge, so both pieces usually travel together. Different frameworks provide different export formats, but the goal is the same. Produce a portable artifact that another runtime can load. TensorFlow commonly uses save model, while PyTorch often exports to ONNX for interoperability. Even when deployment is not your job, understanding the usage pattern changes how you think about constraints. A model meant for fast online decisions has very different needs from one meant for offline analysis. The remaining topics separate common misconceptions from the main serving patterns. Inference is simply the act of generating predictions, and the next step is to compare online prediction with batch prediction. Where the computation happens changes the design of the whole system. Running on a device puts constraints on memory, power, and connectivity, while running in the cloud shifts those concerns into the service infrastructure. Some of these deployment ideas are technical and unfamiliar, especially if the background is academic. A dense section can be set aside and the rest still makes sense because the topics are organized in independent pieces. Deployment for machine learning has its own rules, and that makes a few common assumptions misleading. The goal here is to clear those up so the process feels more realistic and less intimidating. A model does not behave like ordinary application code because it depends on data, model drift, and the quality of its predictions over time. That difference is why deployment can feel harder than expected and why experience matters when planning for it. Large ML systems usually manage far more than a couple of models, so the production stack has to handle scale, variety, and constant change. Academic work often pushes toward a single, narrow problem, so it is easy to imagine one model sitting behind one application. Production systems break that assumption quickly because different features, regions, and use cases each create their own model needs. A ride-sharing platform needs separate models for demand, pricing, fraud, arrival time, churn, and more. Once you add multiple countries and local behavior, the count grows fast, and a system built for one or two models no longer fits the real workload. The main thing to look for is breadth, recommendation, ranking, personalization, search, and many other tasks all depend on machine learning. A company at this scale is not managing one model pipeline, but a whole collection of models with different inputs, outputs, and refresh cycles. The figure reinforces the same point from a different angle. One product can contain many separate ML jobs, each solving a different business problem. That is why platform design has to support a portfolio of models, not a single deployment path. Real production environments often reach the thousands. At that point, the challenge is no longer whether a model works, but how to train, deploy, monitor, and update many models at the same time without losing control. Model performance does not stay fixed just because the code stays unchanged. Once a model is deployed, the world around it keeps changing, and that can quietly change how well the model works. Software rot is the slow decline of a system even when no obvious edits are being made. In production, small environment changes, dependencies, and infrastructure drift can still make a stable-looking system less reliable. Machine learning adds another layer to that problem. The input data in production can drift away from the data used for training. When that happens, the model is facing a different world than the one it learned from, so its performance often starts strongest right after training and then slowly degrades. Model updates are not a rare maintenance task. They are part of keeping performance alive in production. The main idea here is that staleness is a real failure mode, so update speed matters just as much as model quality. The useful question is about capability, not preference. If the pipeline is ready, faster updates let the model respond to changing data before accuracy slips too far. A model's behavior drifts as the world changes, so long release cycles create avoidable lag. DevOps already solved part of this problem by making deployment frequent and routine, and ML teams should borrow that habit instead of treating every model release like a special event. Monthly or quarterly retraining is often too slow when the underlying data shifts quickly. Minutes-level iteration shows the goal. Shorten the loop until the model can keep up with the product and the users. That quote captures the engineering mindset behind this whole idea. The bottleneck is rarely just the model itself. It is the process that turns a good model into something safely shipped and continuously refreshed. The exact retraining schedule depends on the data, the risk, and how quickly the environment changes, so there is no single magic interval. The deeper point is to treat retraining as an operational decision, not a yearly planning exercise. Scale matters as soon as a model has to serve real users, real traffic, or real business demand. The point here is to separate a small demo from a system that must keep working when usage grows. The exact threshold changes from one product to another, but the idea is always the same. The system has to handle more demand than a single-person prototype. Once requests come in continuously, latency, throughput, and reliability start to matter. It may feel like only a few giant tech companies face scaling problems, but many engineers work inside larger organizations of some kind. A company with 100 employees is already much more likely to have production systems, active users, and ML features that must hold up under load. The useful part of this figure is the concentration in larger companies. The bars on the bigger company side tell you that scale concerns are not reserved for the very largest names. They show up wherever software teams support substantial products. This figure supports the argument with survey data rather than intuition alone. It gives a quick visual reason to expect that many engineers, including ML engineers, will end up working on systems that need to scale. That pattern carries over to ML roles as well. So the practical conclusion is straightforward. Scalability is not a niche concern. If a model is part of a product used by many people, the ML engineer needs to think about how that model behaves under load and growth. Prediction serving choices shape latency, infrastructure, and how fresh the results can be. The main question is whether predictions are produced on demand or prepared ahead of time. The terminology around prediction serving is messy, so the useful move is to focus on the operating mode. The important distinction is whether the model needs fresh request time data or whether it can work from features that were already computed earlier. The first mode is the simplest operationally. The model runs over a set of examples together, and the results are produced in a group. That works well when users do not need an immediate answer at the moment of the request. In that setup, every input to the model comes from data that was prepared in advance. No live event data is needed at prediction time, which keeps the serving path simpler. The next mode still serves predictions at request time, but it relies only on pre-computed data. The request arrives, the service looks up the stored features, and the prediction comes back immediately without waiting for new feature computation. A common example is a vector representation or embedding that was built earlier and saved for later use. The serving system stays responsive because it is reading from existing features rather than building them on the spot. The third mode adds live information to the stored features. That gives the model access to the most recent state, which matters when a current event can change the prediction. This is the most flexible setup because the model combines history with fresh signals arriving in real time. It is the right choice when the prediction depends on what is happening right now, not just on what was known earlier. Online prediction means the system waits for a request and returns a result immediately. A translation service is a good example. The request comes in, the model runs, and the response is sent back in the same interaction, which is why this style is also called synchronous or on-demand serving. Batch prediction flips that flow around. The model runs ahead of time, stores the results, and users read those stored predictions later. That pattern works well when many people need similar outputs, and the system can tolerate a delay between computation and retrieval. The naming around prediction modes is messy, and that matters because the wrong term can hide the real system design. The key idea here is to separate how predictions are served from whether data arrives in chunks or one request at a time. Both pairs of terms try to describe how prediction requests move through the system, but neither pair is perfectly clean. A model can serve many samples at once or one at a time. And if requests travel through a real-time transport, the request flow and the model work can happen asynchronously even when people call it online prediction. The practical distinction is the data available at prediction time. Batch prediction relies on historical data that can be prepared ahead of time, while online prediction can combine that history with live signals that change from minute to minute. The figures below show those two architectures, and the next step is to focus on what counts as a batch feature. Focus on the data flow that ends before the prediction happens. Historical data is collected, features are prepared, and the model scores those prepared examples in batches. The important part is that nothing in this path depends on a live event happening right now. Batch prediction is the straightforward case. Prepare features first, then run the model over a set of records. That separation makes it useful when the predictions can wait and the inputs come from stable, stored data. Track the request coming in, the feature lookup, and the model response going back out. Even in an online system, the model may still rely only on pre-computed historical features. The difference is that the prediction is requested on demand. Online prediction changes the timing, not necessarily the feature set. A request arrives, the system gathers whatever features are already available, and the model returns a result quickly enough to support an interactive application. Historical data gives you stable features such as long-term averages or profiles, while streaming data adds the live context that may matter right now. For a delivery time estimate, that difference is important. Past restaurant behavior tells one story, and current order volume or courier availability tells another. Start with the historical side of the problem. These features are computed from stored data and reused across many predictions until the underlying history changes. Averages like this are classic batch features because they come from past records, not from a live event. They give the model a stable baseline for how long this restaurant usually takes. Now shift to signals that change immediately. These features depend on what is happening right now, so they are useful when the prediction needs to react to current conditions. Recent order load and available drivers are live operational signals, so they belong on the streaming side. Those numbers can change between one prediction and the next, which is exactly why they improve an online estimate like delivery time. Streaming features are a narrower idea than online features, and that distinction matters when you design prediction systems. The main question is whether a feature comes from a live stream of data or whether it is simply used at prediction time. Online features cover anything available at request time for prediction. That can include values computed earlier in batch, stored in memory, and reused when a prediction request arrives. Item embeddings are a common example, especially in recommendation systems. The embeddings may be computed offline, but they are loaded during serving, so they count as online features even though they are not streaming features. Streaming features are stricter. The value must be produced from the live stream itself. That means the feature changes as new events arrive, rather than being pulled from a pre-computed store. That mixed design is common in real systems. A model might use live signals from a stream alongside stable batch features. And some teams call that streaming prediction to distinguish it from online prediction that has no streaming inputs. Track the two input paths in the diagram. One path brings in pre-computed batch data, and the other brings in fresh streaming data. The important idea is that serving can merge both sources before the model produces a result. The figure names the hybrid architecture, and that hybrid is the point to keep in mind. It is not a choice between batch and stream as separate worlds. A serving system can use both at once. A practical system often mixes both modes. Popular queries can be handled ahead of time, while rare or fast-changing queries are scored on demand. So the system uses each method where it fits best. The trade-off is really about timing and system goals. Batch prediction waits, groups work, and favors throughput. Online prediction responds immediately and favors latency, which is why different applications choose different modes. A food app is a good example of the split. Ranking restaurants can happen in batch because the set is large and the result does not need to change every second, but item recommendations after a click need fresh online scoring. That assumption is too simple. Online serving may lose some batching optimizations, but it also avoids spending compute on predictions nobody will ever use. So the real cost depends on traffic patterns and the application. When only a small share of users visit each day, pre-computing for everyone can waste most of the work. In that setting, online prediction saves compute by only scoring the users who actually show up. Batch prediction and online prediction solve the same problem in different ways, and the difference matters whenever latency or scale becomes constraint. The central question is whether a model should answer immediately for each request or produce predictions ahead of time and serve them later. Online prediction matches the usual mental model for ML systems. A request comes in, the model scores it right away, and a response goes back through an endpoint. That works well when you're prototyping or when a service needs a fresh prediction for each individual request. Batch prediction flips the timing around. Instead of paying the model cost when a request arrives, you do the work ahead of time, often for many inputs at once, and save the outputs in a database or table for later use. That shift removes the waiting time from the user-facing path. The request only has to retrieve a stored prediction, which is often much faster than running a complex model at the moment of the request. This approach makes sense when volume matters more than immediate freshness. A company might score every customer, then act only on the top fraction, because not every prediction needs to drive a real-time decision. The weakness is freshness. If a user's interests change quickly, the stored recommendations can stay stuck on the old pattern until the next batch run updates them, which is a real limitation for interactive products. Another constraint is that batch jobs need a known target set. That works for a fixed list of users, but it breaks down when inputs arrive unpredictably, like arbitrary text that needs translation on demand. In some systems, delay is more than inconvenient. It changes the outcome. Trading, driving, voice input, authentication, fall detection, and fraud checks all need a decision while the event is still happening, because a late answer can be useless or even dangerous. So batch prediction is really a practical compromise. If generating each prediction on demand is too costly or too slow, pre-computing them can make the system usable even when the model itself is not fast enough for live serving. As hardware improves and serving techniques get better, the trade-off shifts. When live inference becomes cheap enough, the simpler and more responsive option is to score requests as they arrive. Moving toward online prediction requires more than just a deployed model. A company needs a pipeline that can handle incoming data quickly, and it needs a model that can answer fast enough for the user experience it targets. The first piece is the data path that keeps up with live events, and the second piece is the model itself. That pipeline has to ingest events continuously, compute any streaming features that the model needs, and feed them through the prediction service without much delay. In practice, real-time transport plus a stream processing engine is what makes that flow possible. Once the data can move quickly, the remaining bottleneck is how fast the model can score it. For consumer-facing systems, even a short pause can feel slow. Millisecond-level inference is often the difference between a smooth interaction and one that feels laggy or unresponsive. Stream processing is one part of the bridge between batch and live serving, and model optimization is the other. Once the pipeline can move data in real time, the next question is how to make inference itself cheaper and faster. Batch and streaming systems solve the same modeling problem in two very different ways, and that split becomes a source of production issues. The goal here is to understand why ML systems often end up with separate paths for training and inference, and why unifying them matters. Large-scale data processing was dominated for years by batch tools such as MapReduce and Spark, so teams naturally reuse them for machine learning. That works well for periodic jobs, but online prediction needs fresh features all the time, which pushes the system toward a second streaming pipeline. For a trip time model, a feature like average speed in the last 5 minutes looks simple, but the computation depends on time. During training, you can compute it over a data frame from past data. During inference, the same idea has to run continuously over a moving window as new traffic arrives. That duplication is dangerous because the batch path and the stream path can drift apart. If one team changes the feature logic and the other side does not, the model trains on one definition of the data and serves on another, which creates hard-to-find bugs in production. The important relationship in the figure is the split between the offline path used for training and the online path used for serving. The more separate those paths are, the more chances there are for the feature computation to diverge. That diagram makes the maintenance problem very concrete. One side supports model development, the other side supports live prediction. When those responsibilities live in different teams, consistency becomes a systems problem, not just a modeling problem. The wider pipeline adds more moving parts than the simplified workflow many people know from research. The research box is the familiar part, but production has to include data collection, feature computation, serving, and a feedback loop that keeps the system working online. The key thing to watch in the figure is that the academic-style workflow sits inside a larger operational system. Real prediction services have to connect data sources, feature generation, and deployment infrastructure around that core modeling step. This broader view matters because online ML is not just about a model file. It is about a pipeline that can produce the same features reliably in both training and serving, while still handling fresh data at production speed. A lot of modern ML infrastructure work focuses on making one processing stack serve both offline and online needs. Systems like Flink and feature stores that centralize feature definitions reduce the gap between training features and serving features, so the same logic can be reused with less drift. Model compression is about shrinking a model so it is cheaper to run at prediction time. That matters when latency, memory, or deployment size become the bottleneck. A streaming pipeline can deliver fresh features quickly, but the model still has to answer fast enough to be useful. Online prediction depends on both pieces working together: fast feature extraction and fast inference. Those are the three levers you can pull. Sometimes the best fix is to optimize the computation, sometimes to reduce the model itself, and sometimes to move to better hardware. These two ideas are related, but they are not the same. Compression reduces the size or complexity of the model, and that often speeds up execution as a side effect. Originally, the big motivation was fitting models onto small edge devices. The other two paths matter too, but they belong in different discussions. Optimization techniques on one side and specialized hardware on the other. The rest of this part stays on the question of how to make the model itself smaller. This area is moving quickly, and the tool set keeps expanding. Even so, for methods show up very often. Low-rank optimization reduces redundant structure. Distillation transfers behavior to a simpler model. Pruning removes unneeded weights, and quantization uses lower precision numbers. Low-rank factorization reduces a large model by replacing a high-dimensional object with a smaller one that captures most of the useful structure. That matters because fewer parameters usually means less memory, faster computation, and easier deployment. The idea is to keep the important signal and throw away redundancy. In neural networks, that often means breaking a large filter or tensor into a smaller representation that is cheaper to store and faster to run. A small filter can sometimes approximate the effect of a larger one, especially when the architecture is designed for that compression. SqueezeNet uses that kind of replacement to cut parameter count very aggressively, while keeping accuracy close to a much larger network. MobileNets uses a different decomposition. First, it applies a separate spatial filter to each channel. Then it mixes channels with a one-by-one convolution. That breaks one expensive convolution into two cheaper steps. And when the kernel is 3 times 3, the parameter savings are large. Track the 2 stages in the figure. One stage handles spatial filtering inside each channel, and the other stage combines information across channels. The point is not to do all the work in one heavy filter, but to split the job into simpler pieces. That diagram ties the algebra to the architecture. The standard convolution is replaced by a depthwise step and a pointwise step, and together they form a depthwise separable filter. These methods can make models much smaller and faster, but they are not universal tricks. They depend on the model family and on careful architectural design, so they work best when you already know the structure you want to compress. Knowledge distillation transfers behavior from a large teacher model into a smaller student model. So the model you deploy can stay compact while still keeping much of the teacher's performance. The main idea is to train a smaller network to match the outputs of a stronger model, instead of learning only from the raw labels. That often gives the student richer guidance and can produce a model that is much cheaper to run, like distillBERT, which keeps most of BERT's language ability while becoming smaller and faster. A useful feature is that the teacher and student do not need the same architecture. So a transformer can teach a random forest if the training setup is designed that way. The trade-off is that you need a good teacher available first. And if you do not already have one, You pay the cost of training that larger model before the student can learn from it. Pruning reduces a model by removing parts that contribute little to the final prediction. In tree models, it means cutting away weak branches, and in neural networks the same idea helps shrink unnecessary complexity. The original idea comes from decision trees, where whole branches can be removed if they do not help classification. Once neural networks became common, the same pressure showed up there too. Many models have far more parameters than they really need, so pruning became a way to cut wasted work. There are two ways to think about pruning in neural networks. You can remove entire nodes, which changes the architecture, or you can keep the architecture and zero out weights that matter least. That second form is more common. The model stays the same shape, but becomes sparse, which saves storage and can make inference faster. That question is still debated. Some researchers argue that pruning is really a way to discover a better architecture, so the sparse result should be retrained from scratch. Others find that the pruned sparse model itself can outperform the retrained dense version. The practical lesson is that pruning can help in more than one way, but its exact benefit depends on how you use it. Quantization reduces model size and usually makes inference faster by using fewer bits to store and process numbers. It shows up across many architectures because the same idea applies whether the model is for vision, language, or something else. That broad applicability is the main reason quantization appears so often in practice. A compression method that works across tasks and model types is much easier to adopt than one tailored to a single network design. A parameter stored in 32 bits takes twice as much space as the same parameter stored in 16 bits, so the memory savings are immediate. For a large model, that difference can be hundreds of megabytes, and it also lowers the pressure on hardware during training and inference. As precision drops, the representation gets smaller and more aggressive. Half precision is a common compromise. 8-bit integer models push farther, and 1-bit schemes are the extreme case where each weight carries almost no numerical detail at all. Speed improves for two reasons. The model may fit a larger batch, and each arithmetic operation can be cheaper when the numbers are smaller. Even a simple addition illustrates the point, because 16-bit arithmetic usually takes less work than 32-bit arithmetic. The cost of fewer bits is that values must be squeezed into a narrower numeric range. That introduces rounding and scaling error, and if the range is too tight, values can collapse to zero or blow past the limits of the format. Quantization can be applied while the model is being trained, or after training when the model is converted for inference. Training with lower precision saves memory during optimization, while post-training quantization is the simpler route when the goal is deployment. Hardware support has made this much more practical. Tensor cores and TPU float 16 support let modern systems train efficiently with reduced precision. So low-precision methods are no longer just experimental tricks. On-device deployment often depends on fixed-point arithmetic because the hardware is limited and the power budget is tight. Frameworks such as TensorFlow Lite, PyTorch Mobile, and TensorRT make post-training quantization a routine deployment step. A production example makes the trade-offs easier to see. Latency, throughput, model size, and precision all interact when a system has to serve real traffic at scale. Roblox needed very high request volume with strict latency limits, so they improved the serving stack step by step. They moved from a large BERT model to distill BERT, switched from fixed shapes to dynamic shapes, and then applied quantization for another large gain. Track the bars in order. The baseline sits highest, and each compression step lowers latency. The important comparison is how much more the quantized model cuts response time after the model has already been simplified in other ways. The figure ties the serving story together by comparing the effect of each optimization step. The main question to keep in mind is which change removes the most latency for the least loss in model usefulness. That jump is the clearest evidence for why quantization is so widely used in deployment. Moving from 32-bit floating point to 8-bit integers can cut latency dramatically and let the system handle many more requests in the same time. Speed alone does not tell the whole story. A compression method is only useful if the model still produces acceptable predictions. So the missing quality comparison is an important caveat in interpreting the results. The main question here is where the model does its work, on remote servers or on the device itself. That choice affects cost, latency, privacy, and even whether the application can run at all. Cloud deployment means the heavy computation runs on server infrastructure, while edge deployment pushes that work on phones, browsers, cars, cameras, and other devices. The difference matters because it changes who pays for the compute and where the data has to travel. For many teams, the first step is to package the model and send it to a managed service like AWS or GCP. That path is popular because it removes a lot of operational work and gets a model into production quickly. The trade-off is cost, and machine learning can burn through compute very quickly. Once inference traffic grows, cloud bills can become large enough to hurt a startup or force a team to rethink the whole architecture. Pushing part of the workload onto edge devices reduces how much work the cloud has to do. That lowers server usage, which is one of the most direct ways to bring the bill down. Edge deployment also helps when network access is poor or unavailable. If the model runs on the device, the application can still function in rural areas, in low connectivity regions, or inside organizations that do not allow internet dependence. Another benefit is speed over the network path. Even if the model itself is fast, sending data to the cloud and waiting for a response can dominate the delay. So keeping inference local can make the whole interaction feel much quicker. Privacy is a major reason to prefer the edge. When user data has to move across networks or sit alongside many other users' data in the cloud, the exposure risk rises, and a single breach can affect a lot of people. Keeping data on device can make regulations easier to satisfy because fewer transfers and centralized stores are involved. Even so, privacy is not automatic, since a stolen device can still expose the data it carries. The device still has to be capable enough to run the model. That means enough processor power, enough memory to load it, and enough energy to keep the application alive without draining the battery too quickly. Those constraints are pushing companies to build better chips for ML workloads. As more specialized hardware appears, the number of active edge devices keeps growing, and the ecosystem around edge inference gets bigger very quickly. That question leads to compilation and optimization for specific hardware backends. The next idea is to watch for intermediate representations and compilers, because they make it possible to adapt one model to very different devices efficiently. Getting a model onto edge hardware means more than saving a file. The real challenge is making framework code fit the hardware backend and run fast enough to be useful. A model only runs on a backend if that backend knows how to handle the framework's operators. That is why support gaps matter so much. Without them, the model may be trapped on the wrong platform even if the hardware itself is available. Supporting one framework across many chips takes real engineering work, because each chip has its own way of storing data and doing arithmetic. The same model operation can need a completely different implementation on different hardware. The key idea in the figure is that CPU, GPU, and TPU are not just faster or slower versions of the same thing. They organize computation and memory differently, so efficient code has to match the structure of the chip. That difference explains why vendor support is so hard to generalize. A backend compiler has to understand the shape of the hardware, not just the syntax of the framework. A scalar CPU, a vector-style GPU, and a tensor-style TPU all want the same math expressed in different ways. Convolutions and memory access patterns have to be rearranged carefully, or the chip spends its time waiting instead of computing. Because of that complexity, support tends to concentrate around a small set of popular combinations. Bringing up a new device usually means writing kernels, tuning them, and doing a lot of hand integration. A bridge layer reduces that duplication. Frameworks can speak one internal language, and hardware vendors can optimize for that same language instead of chasing every framework separately. That shared language is the intermediate representation, or IR. Compilers lower model code into IR first, then transform it step by step until it becomes machine code for the target device. The flow in the figure is the important part. The compiler does not jump straight from model code to final instructions. It passes through multiple IR stages, so each stage can simplify, reorganize, and optimize the computation. Those intermediate stages give the compiler room to reason about the model before it commits to a specific chip. That is what makes hardware-specific code generation possible. Lowering is a transformation, not a simple line-by-line translation. The compiler reshapes the program because there is usually no exact one-to-one match between framework operations and hardware instructions. At the top level, the compiler usually thinks in graphs rather than in raw instructions. A computation graph shows which operations depend on which others, and that structure is what later optimization passes can analyze. Once the model has been lowered, the next question is performance. A program can run on a chip and still waste most of the hardware's potential, so the compiler has to look for speedups. Running is not the same as running well. The generated code may miss cache locality, move data too often, or fail to use vector and parallel execution units that the chip already provides. Real pipelines are usually stitched together from many libraries. Data might move from feature extraction to vectorization to a pre-trained model and then into an ensemble, and every boundary adds overhead if the handoff is careless. Even if each library is fast on its own, the whole pipeline can still be slow because data keeps crossing framework boundaries. That is why end-to-end optimization matters. The cost of movement can dominate the cost of computation. That gap is common in practice. Teams build something that works, deploy it, and only then discover that the hardware behavior is the real bottleneck. So optimization becomes a separate job. The job is broader than tuning a single model. It often includes model design, hardware feedback, and compiler collaboration because all three pieces affect the final runtime. The company description makes that role concrete. The team is responsible for making the models fit the hardware and for feeding practical requirements back into the compiler and silicon work. Quantization and retraining help models survive the move to smaller, faster hardware. If precision drops or the model becomes fragile, these tools help recover accuracy while keeping the model efficient. Compiler features can be designed around the flexibility of neural networks themselves. That means the compiler is not just executing a model. It is using the model structure to create better execution paths. Sometimes the model is adjusted for the machine rather than the other way around. In that case, the architecture itself is chosen or designed to fit the hardware's strengths. Customer feedback matters because the useful constraints are often outside the lab. Engineers have to balance performance targets, deployment limits, and the practical needs of people building real systems. That shortage of hardware and ML experts is exactly why optimizing compilers matter. They can inspect the graph, recognize expensive patterns like convolutions and loops, and apply speedups automatically. A local optimization targets a small region of the graph, often a single operator or a small cluster. A global optimization looks at the full graph and tries to improve the entire execution plan end to end. Local optimizations usually try to do more work at once or reduce wasted data movement. The four common techniques that follow are standard tools compilers use to get there. Vectorization changes the unit of work from one element at a time to several elements packed together. That matches the way many chips are built and can cut overhead from repeated loop steps. When the data is laid out contiguously, the machine can process a chunk more efficiently than a single scalar value. The gain comes from reducing the cost of repeated loads, stores, and loop control. Parallelization splits work so separate pieces can happen at the same time. If the chunks are independent, the hardware can use more of its available execution capacity. The important condition is independence. Once each chunk can be computed without waiting on the others, the compiler can spread the work across cores or accelerator units. Loop tiling changes the access pattern so the compiler works on blocks of data that fit the hardware better. That helps caches stay useful and keeps memory traffic under control. The same loop can behave very differently on different hardware. A pattern that is friendly to one architecture may fight the memory system on another, so this kind of tuning is hardware specific. Fusion reduces the number of times data has to move through memory. Instead of treating each operator as a separate pass, the compiler combines them when that saves work. If two operations touch the same array, separate passes mean repeated memory traffic. Fusing them keeps the data in place longer and removes the extra loop overhead. The figure matters because it shows the difference between separate operators and one combined kernel. The key relationship to track is how many times the data has to be read and written. That diagram is the simple case. One fuse path replaces multiple separate ones. The same idea becomes much more valuable when the graph is larger and the memory cost is higher. Big gains often come from looking past one operator and optimizing whole graph patterns. In convolutional networks, vertical and horizontal fusion can remove extra memory movement across several stages. The important parts in the figure are the sections that get merged. Track how the computation graph is simplified because each merge removes another place where data could be written out and read back in. That kind of graph-level fusion is where the bigger performance gains come from. The compiler is no longer tuning isolated operators. It is reorganizing the whole flow of computation. Once a graph has many valid execution choices, hand tuning stops scaling. Machine learning becomes useful because it can search a large space of choices and learn which ones are likely to run faster. A computation graph is rarely fixed to one schedule. Even with just three operators, the compiler may have several plausible fusion choices, and each choice changes the runtime behavior. Traditionally, experts build rules from experience and hardware knowledge. That can work well for one target, but it depends heavily on the person and on the exact model they have optimized before. The weakness is clear. A rule that works well in one place may not be best, and it may not transfer cleanly to a new chip or framework. Every new target forces a lot of manual work. A convolutional network, an RNN, and a transformer do not expose the same bottlenecks. That is why vendors often focus on popular models first, while new architectures may need to prove their own speed before getting broad support. Trying every path would explode combinatorially, so the search has to be narrowed. ML helps by estimating which paths are worth testing and by predicting runtime without fully executing every option. Full graph timing depends on too many interacting assumptions. It is much more practical to model smaller pieces where the compiler can make cleaner estimates and learn more reliable patterns. CUDNN Auto-Tune is a familiar example. It tries a limited set of convolution implementations and picks the fastest one. Auto-TVM is broader because it searches over subgraphs, trains a cost model from real runtime measurements, and can adapt to different hardware. The first step is to break the graph into manageable pieces. Splitting the graph makes the optimization problem smaller. Each subgraph can be searched and scored separately instead of forcing the compiler to reason about the full model at once. The second step estimates how large each piece is. That size estimate helps decide where the compiler should spend effort. Bigger or more expensive pieces deserve more search time because they have more impact on the final runtime. The third step allocates search time where it matters most. Now the compiler can spend its budget intelligently. It does not brute force everything equally. It gives each subgraph a controlled amount of exploration. The final step combines the best pieces into one executable graph. After each piece is tuned, the compiler reconnects them into one schedule for the whole model. The goal is a complete execution plan, not just a set of isolated wins. The useful part of Auto-TVM is that it learns from real measurements instead of pure guesswork. That makes it adaptable to new hardware, although it needs time to gather enough data before the model starts making good predictions. The search may take hours or even days, especially for complex models. That cost is acceptable when the tuning is done once and reused many times on the same hardware family. The performance curve in the figure shows the trade-off clearly. Auto-TVM needs several trials before it overtakes CUDNN, but once the search has learned enough, it can produce a better result for that model and device pair. The important detail is the crossover point. Early on, the tuned search is still learning, but after enough trials, its chosen path becomes faster than the hand-engineered baseline. Browser runtimes make models portable across phones, laptops, and tablets, so deployment stops depending on the chip inside the device. The big advantage is reach. One browser-based model can run on a MacBook, a Chromebook, an iPhone, or an Android phone without rewriting for each chip family. That removes a lot of hardware-specific deployment work, especially when device makers change architectures over time. JavaScript is the language people naturally associate with the browser, and tools like TensorFlow.js, Synaptic, and Brain.js make that route possible. The limitation is speed and expressiveness. Once the computation gets heavier, JavaScript becomes a poor fit for feature extraction and other demanding parts of pipeline. WebAssembly gives a stronger path because it runs compiled executable code in the browser instead of pushing all the work through JavaScript. A model built in scikit-learn, PyTorch, TensorFlow, or another framework can be compiled to WASM, then called from JavaScript when the browser needs to use it. That combination is why WASM has gained so much attention. It is practical to use, it performs well, and the browser support is already broad. When a technology reaches that kind of coverage, it becomes realistic to rely on it for everyday deployment. The cost of that portability is speed. Even though WASM beats JavaScript, it still trails native iOS or Android code, and benchmarks have shown sizable slowdowns compared with running directly on the device. Deployment shifts the hard problem from model fitting to systems engineering. And that change matters because real-world performance depends on latency, cost, reliability, and hardware limits. A model can be accurate and still fail in production if the surrounding system cannot serve it reliably. The chapter makes that distinction clear. Deployment is about building the infrastructure that lets the model actually work for users. Two choices keep coming up: whether predictions happen immediately or in batches, and whether they run on the device or in the cloud. Each choice trades one constraint for another. So the right answer depends on responsiveness, flexibility, and how much delay the system can tolerate. Cloud deployment removes a lot of local complexity, but network delay and usage charges can become the bottleneck. On-device inference avoids that network round trip. It only works when the hardware is strong enough to handle the model within tight limits on power and memory. Most of the pressure in these deployment choices comes from hardware limits. As chips get faster and more specialized for machine learning, the balance shifts towards serving predictions directly on the device, which reduces delay and keeps more computation close to the user. The figure captures that direction of travel. Stronger hardware makes local inference more practical, so the model can move closer to where the data is generated. The important idea is the path from centralized cloud serving toward device-level prediction. That shift changes the deployment target, not the need for good engineering. The closer the model gets to the user, the more the system depends on efficient execution and careful resource use. Getting a model into production is only the beginning of the operational work. After release, the real question becomes whether the model keeps behaving well as data changes, traffic grows, and failures appear in the system around it. Development environments matter because the tools and setup around the model affect how teams build, test, and ship changes. Good infrastructure makes it easier to reproduce work and avoid surprises when code leaves the notebook. Containers help package the model and its dependencies so the same software can run in different places with fewer environment mismatches. That kind of consistency becomes important once the model has to survive outside a single developer machine. Those demos are useful because they show how these deployment ideas appear in real systems, not just in theory. Real projects reveal the engineering trade-offs that examples on a page often hide. Serialization controls how model inputs and outputs are packaged for transport and storage. Once a prediction service starts talking to other services, the format of the data becomes part of the deployment problem. That talk is a good example of infrastructure built around people and production needs rather than around a single model. It shows how organizations design systems so machine learning can serve many products and teams at once. This example shows how large companies treat ML as a platform problem. The model matters, but the surrounding services, workflows, and operational controls matter just as much. That case study is valuable because it focuses on failure, not just success. Production systems break in specific ways, and understanding those failure modes is what makes monitoring meaningful. A large collection of deployed models is useful because patterns start to emerge across many projects. The lessons from a company like Booking.com show which deployment issues repeat across teams and products. Industry surveys help show where teams are spending their effort and what pain points keep coming up. They often confirm that deployment and operations dominate far more of the work than people expect at first. Distribution shift is one of the reasons production monitoring matters so much. When the data changes, a model can drift away from the conditions it was trained on and stop making good predictions. DevOps examples are relevant because ML systems inherit many of the same operational concerns as software systems. Reliable delivery, automation, and observability all become part of the model lifecycle. Streaming systems like Flink matter when predictions need to happen continuously as data arrives. That pushes ML closer to the world of real-time data processing rather than offline analysis. Instrumentation gives you the signals needed to tell whether a model is healthy in production. Without that visibility, failures can persist for a long time before anyone notices them. Developer surveys are useful for understanding what tools and practices have actually spread across industry. They give context for why certain deployment patterns and platforms become common. Usage and revenue numbers help explain why serving predictions efficiently matters at scale. Once traffic grows, small choices in infrastructure can turn into large cost differences. The service endpoint is the address that other systems call to get a prediction. That single URL becomes the public doorway into the model, so routing and reliability matter a lot. Cold start cases often need a fallback strategy because the model has little or no history to work with. A simple generic recommendation is sometimes better than forcing an overconfident guess. Batch and streaming systems are not always separate worlds. Some platforms try to handle both with the same infrastructure. That idea matters because it reduces duplication and lets teams reuse the same data pipeline in more than one mode. Compression and acceleration techniques reduce the work a model needs to do at inference time. That is one of the main ways to make deployment feasible on smaller or cheaper hardware. Low-rank methods shrink the computation inside neural networks by replacing expensive operations with cheaper approximations. The goal is to preserve useful behavior while making the model faster to run. Smaller models can still be useful when the architecture is designed carefully. This example shows how aggressive size reduction can make a network much easier to store and deploy. Mobile-oriented architectures are built for environments where compute and memory are limited. The design goal is not just accuracy, but a balance between quality and efficiency on a phone or similar device. Distillation transfers knowledge from a larger teacher model into a smaller student model. That gives you a compact model that can be cheaper to run while keeping much of the teacher's behavior. Transformer models can also be compressed for deployment. The important idea is that a smaller version can preserve enough language understanding to be practical in real systems. Pruning removes parts of a network that contribute little to its final behavior. The analogy is simple. Cut away the unneeded pieces so the remaining model is lighter to execute. The lottery ticket idea says a large network may contain a smaller sparse subnet that can still train well. That possibility is one reason pruning has been studied so heavily. Survey papers like this are useful because they separate what has been proven from what is still uncertain. Pruning is promising, but its practical value depends on the model and the deployment setting. Not every compression trick gives the same payoff in real systems. Some methods look attractive on paper, but the actual gains can be smaller once the full deployment pipeline is considered. That question captures the trade-off well. Pruning can help, but it is not automatically the best optimization tool. The right choice depends on whether the savings are worth the complexity. Using very low precision weights can make inference much cheaper to compute. The challenge is keeping enough accuracy while the model becomes more compact and hardware-friendly. That acquisition is a good signal that edge inference became commercially important. When devices do more locally, the value shifts toward efficient models and specialized runtime support. Quantization is about preparing models to run with lower precision numbers. Even when the training procedure is not a full low-bit training scheme, it can still gather the information needed to make later quantization work well. Mixed precision uses different numeric formats where each one makes sense, so training can run faster without losing too much quality. That same numerical flexibility is part of what makes modern deployment hardware so effective. bfloat 16 is one example of a numeric format tuned for machine learning hardware. Formats like this help hardware do more work per cycle while keeping enough range for training and inference. Quantized networks show that lower precision can be used not only during training, but also at inference time. That matters because integer arithmetic is often much cheaper and faster than floating point computation on edge devices. Serving a large model on CPUs shows that deployment constraints are often solved by system design, not just by specialized accelerators. With the right engineering, even demanding models can be made practical at huge scale. Cloud cost is not a side issue. It can become a major business constraint. Once traffic grows or tests run longer than expected, infrastructure spending can rise fast enough to force design changes. Reports like this show that cloud spending is a recurring concern, not a one-off mistake. That is why deployment planning has to include cost from the start. Short experiments can still generate surprisingly large bills if the infrastructure is configured carelessly. The lesson is that cloud convenience needs guardrails, monitoring, and cost awareness. Security is another reason deployment is not just a model problem. Once data leaves controlled environments and moves through production systems, protecting it becomes part of the ML workflow. Slides from a prediction service lecture connect these ideas back to the mechanics of serving models. They help show how the endpoint, data flow, and runtime all fit together in practice. The growth of connected devices explains why edge ML keeps getting more relevant. As more devices produce data, moving inference closer to the source becomes more attractive. Compiler technology matters because deployment performance often depends on how the model is lowered and optimized for the target hardware. A good compiler can turn the same model into a much better runtime program. Modern processors include specialized instructions that speed up machine learning workloads. Those features are one reason the hardware landscape keeps moving toward more efficient inference and training. Systems for data analytics face similar optimization problems. Move less data, do less repeated work, and fuse operations when possible. The same thinking applies when serving ML models efficiently. Loop tiling is a low-level optimization that improves how code uses memory caches. These details matter because hardware performance often depends as much on memory access as on raw compute. Operator fusion combines adjacent operations, so the system does less overhead between them. Runtime adaptation then adjusts execution to better match the hardware and the workload that is actually running. Inference engines often fuse common layers like convolution, bias, and activation into one efficient kernel. That reduces memory movement and makes the same model run much faster on supported hardware. A benchmark can tell you how one model behaves on one piece of hardware, but that does not guarantee the same result for another model. Some numbers look great only because the benchmark model was tuned unusually well for that setup. TVM is another example of the compiler approach to ML deployment. The core idea is to automate optimization so the model can run efficiently without handwritten hardware-specific code for every case. WebAssembly tools matter because they offer another route for portable execution. That portability can simplify deployment when the same computation has to run across different environments. Compatibility checks matter whenever a runtime has to work across browsers or platforms. Deployment choices are often limited by what the target environment can actually support. Performance comparisons between WebAssembly and native code help separate portability from raw speed. That trade-off is central to deployment. The most portable option is not always the fastest, so the target environment has to guide the decision.